video will present the main issue, identify the floating system, the site analysis, the climate analysis, and describe the concept of the floating project. After that, mention the main 3 proposed skin strategies design, finally present the IS simulation assessment and their results. Today, a challenge facing the world which is much faster than ever before due to increasing carbon emissions and rising global average temperature, leading to melting glaciers, more flooding and rising water level. By 2050, the most low-lying coastal cities will face a projected sea level rise by at least half meter. This puts millions of people at risk from impacts of rising seas. These challenges have forced architecture to shift from land into water, and creating a sustainable future vision by improving floating building systems. The following presents the main principles for construction floating building, mega float pontoon type floating. A huge plate placed on the sea level. The pontoon using concrete composite with expanded polystyrene lightweight material. The access bridge, the chain mooring piles for more stability and fixed due fluctuation of the water level, mooring facility to maintain the floating structure in place. The breakwater for mitigation wave forces affecting the floating structure. The proposed location for building a floating resort is Netherlands. Netherlands is located in the northwest Europe, along the North Sea. Netherlands in Dutch literally means the low country. The most lands are reclaimed and coastal lowland. The Texel Island, which is the selected site of the floating resort. It's one of the largest island group along the Wadden Sea Islands in the north of the Netherlands. It's located in the north-northwest of the Netherlands, about 12 km north of Den Helder, along Oudshoel town. The proposed site is connected to the main roads and neighborhood facilities in Oudshoel town. Texel Island has extensive network of cycle paths. It's common for the seals, sandy beach, dunes, grass-topped, near to the fishing harbor. Texel Island has a wealth of natural and cultural landscape. The weather conditions of Texel Island is mist impacted by the Wadden Sea and the North Sea surrounding. The following analysis best describe the climatic conditions. The sun path will be from the northeast side of the building to the southwest, while the dominant blowing wind direction is from the southwest, cold wind. The proposed site is open location, is exposed to the wind and tide, which can be beneficial for employing renewable energy source. We can clearly notice the sun angle during summer and winter solstice. The sun path of the building between sunrise and the sunset with very low solar radiation angle during winter solstice. The highest recorded temperature on June is about 88 degrees Fahrenheit, while the lowest temperature on February is about 18 degrees Fahrenheit. The most wind prevailing with the strongest wind is from the southwest direction, with about 50 meters per hour recorded the highest value on November. Maximum tidal range is about 2.22 meters, while the lowest tide height is about 1.5 meters. The water temperature peak of the Wadden Sea around 16 degrees Celsius on the August, while the minimum temperature ranges about 2 degrees Celsius on February. The water along the coastal of the Wadden Sea is about 2 to 25 meters. Texel Island's geomorphology is endless provenance to motivate my inspiration. The dune floating resort is not only sitting on the water, but it also responds with surrounding environment. Divided into 4 stages, the island segment exposed to natural power source, resulting to lose its stability, then split into 3 different layers, a drift growing in displacement by rising the tidal current, finally the dune sediments accumulation, and created the final form. The design of the project attempted to achieve these goals. floating building includes 3 different levels: the ground floor, the first floor, and the observation room underwater. The variety of the differential levels within the space motivate to the guest for more exploring, as well as keep flowing circulation by altering access from one zone to another. The ground floor includes the main spaces: lobby, living room, dining, and kitchen. The living room surrounding with large glass wall connected with the open space for enhancing visual daylight, and the mesh deck for relaxing. The swimming pool open to the wide view of the sea. The first floor elevated by light stair to the bedrooms. As you step into the project of 6 units of floating buildings, you enter the main building, which represents the entrance of the project, gently stretching to floating farm by curved jetty, with 6 units distributing in radial rounded form. The floating farm, filled with herbs and flowers, act as a greenhouse, collecting the main water through glazing surface slope into basins. The total weight of a structure and environmental conditions surrounding the structure are the main parameters targeted for designing appropriate structure of a floating building. The construction wall of a floating building has different layers of suitable materials, which are associated with a floating house target in Netherlands. It should be lightweight structure, ecosystem, fire-rated, simple integration, and fit with environment. The building project complied the BREEAM as sustainable assessment method to assess the building performance based on environment, social, and economic sustainable impact through setting the standards for best practice. This section will present the modeling design for the base case and the 3 proposed skin strategies with their selected material cladding. All materials of the floating building associated with Netherlands Building Code. The base case construction can be described as shown in the figure. It is covered by aluminum composite panel, opaque panels, silver powder coated, connected together piece by piece as large cladding materials, with large segment of double glazing. The first skin strategy is designed for enhancing energy performance. The envelope design divided into different segments: a transparent surface of double skin facade and opaque surface of vertical and horizontal cedar red western larch wood strips, which adequate for cladding. Glazing surface act as box window, which consists of cavity space between 2 glazing surfaces with bottom air inlet flap. The second skin strategy created double skin facade by applying outer inner glazing surface by using ethylene tetrafluoroethylene ETFE film material cushion, which have 2 layers filled with air, which lies behind the glass fiber reinforced polymer ribs structure. Different physical properties of ETFE can improve the performance of building envelope, such as lightweight of material. The double layer of cushion is about 4.5% of common glass, which require lower support structure. The high thermal mass improved insulation properties by achieving conductivity 2.6 watt per meter square Kelvin, high transparency. Design of the third proposed skin strategy is double skin facade of perforated metal panels based on significant architecture design for enhancing the energy performance of building. The external round hollow perforation layer made of copper alloy covered by anodized BFDF powder coating. It can achieve different levels of transparency. Perforation metal layer inspire architects to create new visions, innovative applications. This section will show the daylighting analysis for all strategies by using IES tool for measuring the radiance, luminance, and glare resolution under overcast sky condition on March 21. The average illuminance of the base case is 1984 lux and 0.5 uniformity ratio. We can clearly see higher glare resolution near to the side of the glazing facade. The measurement illuminance values of skin 1 are better than best case value. The uniformity ratio is lower than best case, is about 0.15, while the average daylight factor in luminance is reached to 616 lux. Daylight distribution of contour lines is remarkably noted next to the ribs facade in a strategy design of Skin 2. The high transmittance material of ETFE allow higher daylight penetration in the zone. The average illuminance is 1451 lux, while the uniformity ratio is lower than the base case, is about 0.48. Here is the Skin 3, which demonstrates the most acceptable daylighting performance through adequate distribution of the natural lighting in the room, with deeper lighting across the area to achieve adequate amount of illuminance. The average is reached to 206 lux and 0.35 uniformity ratio. This section will analyze the annual energy performance of all strategies by using integrated environmental solution Apache. The total annual heating loads of the base case is about 48 MW per hour. The highest values recorded during December and January, while the total annual cooling load is about 2.46 MW per hour, and the August achieved the highest value. The total annual electricity is about 22 MW per hour. The reading prediction indicates that the trend value is higher consumption. Design of Skin 1 intended to reduce the total heating loads by 29% and recorded 19.7 MW per hour, which is a remarkable difference. Also, the annual cooling load is lower than the base case, is 2.27 MW per hour. But the total annual electricity have increased to achieve 22.19 MW per hour. The design envelope of Skin 2 improved reduction value of heating loads to reach 37 MW per hour, but it failed in decreasing the annual cooling loads comparing with the base case. The reading is about 4 MW per hour. Skin 2 acts similarly with Skin 1 regarding with the total electricity, which is still higher than the total electricity of the base case. It's recorded 22.91 MW per hour. The third Skin achieved remarkable reduction in the energy performance. The total annual heating loads reduced to reach 227 MW per hour, while the annual cooling achieved the lowest value in compare with other set strategies, resulting in 0.8 MW per hour. The Skin 3 achieved the most efficient reduction in the total electricity loss. It dropped to 18.68 MW comparing with the others. In this section, the chart presents evaluation among the proposed 3 skins strategy in compare with the base case. According to the total electricity, the base case is the highest value, followed by the Skin 2, then Skin 1, while the Skin 3 achieved the highest reduction of the total electricity to the total annual heating loads. The Skin 1 achieved the lowest reduction value comparing with the other strategies. In terms of the total annual cooling loads, the Skin 3 achieved the lowest reduction value in compare with other strategies. The last Skin strategy represents the most efficient skin design of building envelope comparing with others in terms of energy performance. This portion will install 3 proposed PVs on the optimal model by covering 40 meters square on the first floor roof. After installing the PVs with Skin 3 design, it can clearly seen that all types of the PVs reduce the total energy consumption load, and the last type of the PVs, monocrystalline silicon, achieved the best performance by reducing the total energy to 14.3 MW per hour. Mostly the prevalent wind pressure from the southwest pass across building. The following is comparing the internal ventilation of the base case with the optimal Skin strategy. The optimal Skin created passive ventilation system for enhancing the airflow across the area, which is clearly noticed that it demonstrates the higher air circulation distribution than base case along the side wall and below the monitor, while the higher quality air ventilation levels help to maintain comfortable environment and reduction the overcooling loads during summertime. This section compared the base case cluster of all 6 units with the optimal skin strategy applying on the whole 6 units in terms of energy consumption. The total electricity for the base case is 126.7 megawatt per hour, while the optimal cluster layout reduced the total electricity to reach 105 megawatt per hour. Higher reduction is achieved by installing the passive ventilation and integrating PVs to reduce the total electricity to reach to 78 megawatt per hour.